Functions are also essential in physical chemistry. Function is an equation in which one variable depends on the other. If one variable is represented by multiple terms, then terms from set of one variable depends on the corresponding terms from the set of another variable. Suppose H represents the hours of work done by the workers. The wages W of the workers depend on the hours of work. Then, wage is essentially a function of hours. This is read as W is f of H. All the hours of each worker will be the domain of the function, and all the corresponding wages, which are the values of wages, will be the range of the function. Besides variables, functions also have constants and coefficients. In a function, y equals 2x plus 3y minus 1 is a constant, and 2 and 3 are coefficients. Coefficients are basically the constants with variables. There are different types of functions. Some of the types will be discussed here. The functions in which all the exponents or powers of variables are non-zero integers and all the coefficients are real numbers, then a function is called a polynomial function, or simply a polynomial. The linear function is the simplest polynomial in which the highest power of variable is 1. Example is y equals x plus 1. The functions with the highest degree of variables equal to 2 are quadratic functions. Example is y equals x squared. The functions in which the highest degree of variables is 4 are called quartic functions. Example is z equals x squared y squared. Logarithmic functions are also often used in physical chemistry. They are a great convenience when dealing with the exponents. There are two kinds of logarithms which are different from each other only because of their different bases. A commonly used base of logarithm is 10. The logarithm with base 10 is called common logarithm, expressed as log 10x or log x or lgx. Generally, common logarithm is written just as log. If common log of x, which has a base 10, is equal to n, then it can be written as x equals 10 raised to power n. If u is equal to 10 raised to power x, then u is a logarithmic function of x and can be written as log u equals x. Suppose x is a set of whole numbers, then for every value of x, there will be corresponding value of logarithmic function u. In general expression, u equals ax, is a base of the function, and the exponent x is the log of u. This can be written as x equals log a of u, or simply x equals log of u. The other kind of logarithm has a base of e. E is an irrational number equal to 2.718282848 which continues. The logarithm with base e is called natural logarithm, denoted by a symbol ln. Common logarithm and natural logarithm are related to each other as natural log of x equals 2.303 into common log of x. Just to clarify, common log of 10 is equal to 1, and natural log of 10 is equal to 2.303. When natural log is applied on an exponential term, the constant power comes before the natural log of a variable. Two identities of natural log are as follows: the ln of the product of variables is equal to the sum of the ln of individual variables. Secondly, the ln of x over y will be equal to the difference of individual natural logs of variables. If a is the natural log of x, we can write ea equals x. E to power x is important exponential function used in physical chemistry. Some identities of this exponential functions are as follows: e to power x into e to power y into e to power z equals e to power x plus y plus z. E to power x over e to power y equals e to power x minus y. There are also trigonometric and inverse trigonometric functions. Examples are y equals sine x and inverse of sine y equals x respectively. In physical chemistry, mathematical limits are also applied to functions. The limit of a function, y equals k, limit would be written on left-hand side of a function as lim k approaches a and read as limit k approaches a. What this really means is, if one keeps substituting values of k as close to a as possible, just not equal to a, the function y will produce almost exact value for k equal to limit a. Such a situation arrives when a is undefined term, meaning one does not know what a really is. Is it a number or something else? Due to this undefined term, one cannot substitute any sensible value for a in a function. However, one can use values close to a and get an almost correct answer. Conventionally, limits are written with all the functions, but that's really unnecessary. Limits are necessary to be written only with the functions that have undefined components. For example, if there is a function y equals x over x, at x equals 0 and x equals infinity, y will be equal to 0 over 0 and infinity over infinity, the output will be undefined. Such a situation requires that limit must be applied. One may argue that the solution should be equal to 1, because anything divided by the same thing should be equal to 1, but that's not really correct in this case. Mathematical operations cannot be applied on undefined terms. Limits are also used to check if a function is continuous or discontinuous. A function is continuous at an instant, 1. If function is defined at that instant of limit, 2. If function exists at that instant, and 3. If a function is equal to function at limit applied. If a function does not justify one or more of the conditions, then function is a discontinuous function. Suppose a function y equals x plus 1 over x minus 1. At limit x approaches 1, function is undefined because it gives 0 in the denominator. This is enough to know that a function is discontinuous. We can also plot this function for x being integers. Suppose another function, y equals x squared plus 3. Let's see if it justifies 3 conditions of continuity. Limit applied as x approaches 1. 1 squared plus 3 is equal to 4, which is a defined value. First condition is justified. And at f of 1 is equal to 4 means function exists at f of 1. Now for third condition, comparing function with limit applied and function existing at given instant. Since they are equal, therefore, the function is continuous. Both functions can also be plotted. Continuous function has a continuous curve, whereas discontinuous function has a break. Another essential concept of mathematics used in physical chemistry is differentiation. The process of differentiation is to calculate derivatives. Derivative is the rate of change of dependent variable of a system with respect to the change in independent variable. It is expressed by writing letter d with the dependent variable divided by letter d with independent variable. Generally, it would be dy over dx. Let's consider an example of a derivative. If a block is moved to a position r away from its original position, the speed of the movement will be distance over time. In the language of calculus, it is the rate change in the position r with respect to time. Or, speed is the derivative of a position r with respect to time. A graph of several changes in the position of block with respect to time is plotted. The slope of the line would be equal to the speed. Therefore, speed is essentially the derivative of the position of an object with respect to time. An important side note is needed here. Small d essentially represents derivative. The capital delta is a measurable change between final and initial position, whereas small delta is an infinitesimal change or a very small change. As indicated earlier, generally x is considered an independent variable, whereas y is considered a dependent variable. Definition of derivative can be written in terms of x and y. As y depends on x, y is a function of x. The derivative of the function will be equal to f dash of x. The infinitesimal change in x will result in an infinitesimal change in y, then slope will be given as follows. This is the formal definition of a derivative. According to this definition, the minimum rate change in y with respect to x would be calculated by applying limit to small change in x, so small that change in x is almost zero. One might argue, why make it difficult when it can be understood in simple everyday language? But that's not really true, especially when one has to deal with numerous tiny changes. In such situations, the expression above comes handy. Moreover, the use of differentiation also makes it possible to express many properties of systems in terms of derivatives. For example, earlier we learned that the derivative of position with respect to time is speed. If we take second derivative of position with respect to time, that would result in a value equal to the acceleration. The the second derivative would be written as d into dr over dt, or dr squared over d squared t. This second derivative is equal to acceleration. Similarly, many properties of any system are calculated just by taking derivatives. Another important point to be remembered is that derivative of a constant will result in zero because, by definition, constants do not change. Differentiation can be applied on simple as well as very complex functions and can be applied in quicker ways. However, there are particular ways to follow. To summarize the steps of taking derivative, consider an example of a polynomial y equals x cubed. Firstly, the original power is written as a coefficient before the variable x. Secondly, power of the variable is reduced by 1, and thirdly, variable is written with a prefix d. So, the first derivative will be 3x squared dx, which is same as shown here. Its second derivative will be 2 into 3x dx equals 6x dx, which is same as. General form of derivative is dx to power n over dx equals an x to power n minus 1. In Newtonian notation, it is written as f dash of x equals f of x dx. Let's also observe this in Newtonian expression. We have a function y equals x cubed, or f of x equals x cubed. F dash of x is a derivative of the function. As we know, the definition of a function is given here. Replacing with x cubed. Expanding by whole cubed formula. Post of x cubed will be cancelled by negative x cubed. Small delta x is common at numerator, therefore, will be cancelled by the denominator. By simplifying, we get the following. No need to solve the equation any further. Applying limit delta x equals 0 to obtain minimum derivative possible. This gives the first derivative equal to 3x squared, which justifies the general formula. Dx to power n over dx equals an x to power n minus 1. There are many derivatives that are memoized or copied directly from an already prepared document and are used to solve bigger problems. Two of such examples are derivative of natural log of x equals 1 over x, and derivative e to power ax equals or into e to power ax. Since derivatives are the definitions of many properties of systems studied in physical chemistry, thus, are useful to be known. However, some derivatives cannot be found directly. In such situations, chain rule of derivatives is used to find unknown derivatives. Suppose z is a function of y and y is function of x. According to the chain rule, the product of the derivative z with respect to y and the derivative of y with respect to x is equal to the derivative of z with respect to x. Next thing under differentiation is the case of multiple variables. If there are multiple variables in one function, differentiation is applied separately with respect to only one variable. The other derivatives in that instant is treated as constant, and the derivatives obtained are called partial derivatives. Instead of d, curly d is written to indicate partial derivatives. The variables that are kept constant are indicated by writing them at the right bottom of the bracket as shown here. Suppose a function z equals x squared y cubed plus 2y, its partial derivative with respect to x and y will be as follows. First, considering one variable constant, order does not matter. For constant y, partial derivative with respect to x equals 2xy cubed plus 0, and at constant x, partial derivative with respect to y equals x squared 3y squared plus 2, which is equal to 2xy cubed plus x squared 3y squared plus 2. Besides differentiation, integration is also frequently applied in physical chemistry. The derivatives are the small changes in a function expressed separately, whereas integration is the sum of all those small changes. So, integration is the inverse of differentiation. The graph shows all the small changes occurred as delta x. The sum of all the small changes represented by bars is integration. In other words, the total area of all the bars under the curve, from point A to B, is the result of integration, where B is the upper limit and A is the lower limit of this definite integral. The general expression of integration is integral x to power n dx equals x to power n plus 1 over n plus 1 plus c. The stretched s represents the integration sign, x is variable, and the power of variable, and dx represents changes in the function. On the right-hand side, the process of integration involves increase of n by 1, and n plus 1 is written as denominator. At the end, letter c is added to represent a general constant. This is to justify that integration of zero change must be a constant. Couple of examples of integrals are integral x cubed dx equals x raised to power 3 plus 1 divided by 3 plus 1 plus c, which is equal to 1 over 4 into magnitude of x to power 4. And integral 3y squared dy turns out to be equal to magnitude y cubed plus c. The coefficient 3 comes out of integral and is cancelled by 3 at denominator. There can be very complex forms of functions, and their integrals will also not be that simple. The integrals, which are commonly used, but are not so simple to solve, are not solved every time. They are instead memoized and employed directly to solve bigger problems. Examples of such integrals are integral 1 over x dx equals natural log of x plus c, and integral a into e to power ax dx equals e to power ax plus c. The integral with unknown limits of derivatives is called indefinite integral, whereas the integral with specific limits is called a definite integral. An example of a definite integral is shown here. Next topic to be talked about is sequence. In mathematics, we often encounter terms given in sequences. A sequence of terms may have finite number of terms or may have infinite terms. Suppose two sets x and y given here. X equals x1, x2, x3, x4, till x100. Y equals y1, y2, y3, y4, till infinity. Sequence with x terms is a finite sequence because it has finite number of terms. Sequence with y terms is an infinite sequence because it has infinite number of terms. Sequence can consist of variables or constants or of a combination of both. Sequence can be of any pattern. For instance, only odd numbers or only squares, reciprocals, with or without exponents, or a combination of a few or all of these. When terms of an infinite sequence are summed up, it is called a series. The word series is both singular and plural. Series are generally denoted by s. An example of series is as follows. S equals S1 plus S2 plus S3 plus S4 and so on. 1, 3, 5, 7, and so on is an infinite sequence, and 1 plus 3 plus 5 plus 7, so on is a series. Other examples of series are S equals 1 minus 2 plus 3 minus 4 plus, so on, S equals 1 minus 1 over x1, minus 1 over x2 minus 1 over x3 minus so on. 3 dots at the end means the series continues till infinity. Series have essential applications in the field of physical chemistry and in science in general. They play a key role in understanding patterns and structural growths, multidimensional interactions, and the transformations of the patterns in comprehensible forms. Series are infinite, however, they can be computed for their partial sums. Partial sum can be up to any number of terms. This number of terms is usually denoted by n. The partial sum of series would be denoted by Sn. Here's a series, S equals S1 plus S2 plus S3 continues to Sn, plus so on. And the partial sum of this series up to n terms would be Sn equals S1 plus S2 plus S3 continues to Sn. Without 3 dots at the very end. For example, a series of natural numbers Sn equals 1 plus 2 plus 3 plus 4 plus n plus, and so on. The partial sum of this series, up to 10 terms, would be given as S10 equals S1 plus S2 plus S3 continues to S10. Solution will be 55. Similarly, S3 will be equal to 1 plus 2 plus 3 equals 6. Series are also written in short forms. To do so, notation of summation is needed to be recalled or learned. The summation is expressed as follows. Where letter E like symbol is a summation symbol, and at the top of summation represents the number of terms, I represents the nth term, meaning first or second or third, and so on. If express a series in summation notation, we suppose series of natural numbers. S equals 1 plus 2 plus 3 plus 4 plus continues plus n plus, and so on. This can also be written in short form as the partial sum till n equals 10 in short form is, which is equal to 55. Notice that, for complete sum of series, n was equal to infinity, whereas for partial sum of 10 terms, infinity is replaced by 10. There are several kinds of series. Many are named after the names of their discoverers or inventors. Only a few, with their examples, will be introduced here. Constant series. Series in which all the terms are constants are called constant series. Constant series, further, has its own types. Geometric series is a type of constant series. In geometric series, every preceding term has an increment in its power, whereas the base number remains constant. The general form of a geometric series is s equals r to power 0, which is equal to 1, plus r to power 1, plus r to power 2, and so on. Or, in short form, it is. Notice that n, at the bottom, starts from 0th term. An example of a geometric series would be s equals 2 to power 0, plus 2 to power 1, plus 2 to power 2, and so on. And its short form is this. In harmonic series, every preceding term is an inverse of a positive integer. S equals 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus and so on. In short form, it would be written as. Second major class of series is functional series. The terms of a functional series are a product of a constant and a function. It would be of a form as follows. Where x is a variable of the function, the set of all the constant quantities represented by small c are called coefficients in the series, and the set of functions are called basis functions. Such functional series are frequently used in molecular modeling, quantum chemistry, and other similar fields of chemistry, which are all part of physical chemistry. Functional series have particular names and forms. A few examples are introduced here. Power series is a commonly used type of functional series in physical chemistry. This series has a particular form given as shown here. Where h is a constant subtracted from the variable x, the power is changing overall on the difference of variable and a constant. Mind you, this h constant is different from letter c. Not all constants are coefficients. Taylor is of the same form, but Taylor series is necessarily an infinite series. Maclaurin series is also of similar form, the h here is equal to 0, thus, Maclaurin series has the form given here. Another way of classifying series is their convergence. When partial sums, with every preceding term of series, approach to a fixed number, in other words, partial sum becomes closer and closer to a fixed number, series is called a convergent series. Suppose a series. By expanding it, we get s equals 1, plus 1 over 2, plus 1 over 4, plus 1 over 8, and so on. To see if this series converges or not, one usually need to calculate at least few terms of the series. However, in this case, by performing simple algebraic tricks, convergence can be known. If we take 1 over 2 common from all the terms after first, then this series can be written as s equals 1 plus 1 over 2 into square bracket open, 1 plus 1 over 2 plus 1 over 4 plus so on, brackets closed. But as we know, the part in square brackets is equal to series itself, s, therefore, s equals 1 plus 1 over 2s, by solving we get s equals 2. Even if series have infinite terms, the sum of the series turned out to be a fixed number. Thus, it is a convergent series. Series, with their partial sums, becoming larger and larger as one proceeds to the next terms, are called divergent series. Let's test if harmonic series is divergent. Here's the harmonic series. To see if this series diverge, we need to check if, by summing up preceding terms, series become larger or not. S1 is equal to 1, S2 is equal to 1.5, S3 equals 1.833. Now, skipping to the higher terms, S1000 is equal to 7.48547, and S10000 equals 9.68761. As the sum up to 10,000th term consistent increase, thus, harmonic series is a divergent series. There are more kinds of series. Among them, Fourier series is of extreme importance in physical chemistry, which we will be presented later. This video covers topic of mathematics that can help make physical chemistry easier. I put good effort, but I must tell, I am not a mathematician though. Thanks for watching. Kindly let me know your opinion,